Hello, welcome to lecture video 10. This one's about continuous random variables and their distributions. Follows on from lecture 9, which was discrete random variables. Continuous ones are ones that can take any value between certain limits. So for example, speed. If you're in a car driving, your speed can go up and down, and it can be any value between certain limits. A more formal definition is that a random variable x and its distribution are continuous if its cumulative distribution function, capital Fx, can be given by an integral like this. Here's the cumulative distribution function, fx, and here's an integral. It's integrating the density function from minus infinity to x, and that will give us the cumulative distribution function at x. And we've used a different variable here, v, just to distinguish that from the x. The integrand, fx, is the density of the distribution. It's a probability density function. And that probability density function is the differential of the cumulative distribution function. The results that we got for the discrete case, they follow on the same way. So the probability that our outcome will be between a and b, that's equal to the difference in the cumulative distribution function at b and a. That's also equal to the integral of our probability density function between a and b. And finally, the integral of the probability density function over the whole range of possible values must be equal to 1. One difference, though, is that for the discrete case, we had to be careful about defining our intervals, whether these were greater than or greater than and equal to made a difference to the outcome and what we were describing. But they don't make a difference for the continuous case. When you're doing the integral of the function, of the density function between a and b, we don't need to define whether a and b are included in that. It's all the same. So that's a little simpler for the continuous case. So we're just going to look at an example and show this in practice and show how to use it for some simple questions, and that will give you a bit of experience, and then you'll be able to use this type of technique for the sample problems. So here we have a probability density function, fx, which is equal to 0.75 times 1 minus x squared. And that's the definition within the interval x is minus 1 to 1. Otherwise, the density function is equal to 0. So we know the cumulative distribution function is equal to the integral of that from minus infinity to x. And so we can integrate our density function. That's straightforward. And then we can just simplify that, and we get this expression for the cumulative distribution, 0.5 plus 0.75x minus 0.25x cubed. And that's true within the interval that x is greater than minus 1 and less than 1. If we're not in that interval, we have to define it separately. So if x is less than minus 1, the cumulative distribution function is 0. And if x is greater than 1, the cumulative distribution function is equal to 1. So we can sketch what these look like. The blue line shows the probability density function. It stays at 0 until you get to minus 1. Goes up, goes down, and then stays at 0 again when you're greater than 1. Then the cumulative distribution function starts to increase as the probability density function increases, starts to go up, and then it starts to flatten off as the probability density function decreases until it plateaus and it reaches a value of 1 and it stays at a value of 1. So we can use this to answer some questions. The first question, what's the probability of our outcome being greater than a half but less than, greater than minus a half but less than a half? Okay, so we can use these plots to work this out. So if it's greater than a half, greater than minus a half, less than a half, then it's this interval, this region here. We've integrated the density function, and that's the blue shaded area. And so we know that's going to be equal to this shaded area, take away this shaded area. And these two shaded areas we can calculate from the cumulative distribution function. The shaded area here is equal to the cumulative distribution function at 0.5, and the shaded area here is equal to the cumulative distribution function at x is minus 0.5. And so we can see those here, that the shaded area, the probability that our outcome is between minus a half and a half, is going to be the difference between the cumulative distribution function here and the cumulative distribution function here. And so that area is equal to the difference between those two values. So we can work that out now. We put in our values, half and minus a half, plug those into the expression we found for the cumulative distribution function, and that comes out at a probability of 0.6875. The second example along the same lines, what's the probability our outcome is between minus a half and 2, so that would be this interval here. Okay, well that's the cumulative distribution function at 2 minus the cumulative distribution function at minus a quarter. So at 2 we are outside of this interval. At 2 the cumulative distribution function is defined as being 1 up here. So that's 1 minus this expression where we've inputted in minus a quarter for our variable. And we can calculate that, and this comes to 0.6836. So that's just a couple of examples of how to relate the probability density function to the cumulative distribution function, and how you can use these together as you choose to find out the probabilities of certain outcomes if you know what the distributions are. A different sort of question is to say, well, we want to have 95% probability that our outcome is below something, but what would that something be? So we want to say, well, our cumulative distribution function is this. What value are we 95% sure it would be less than? Okay, so the cumulative distribution function equals 0.95, and what value of x corresponds to that? So we can rearrange that equation and find that x is equal to 0.73. That concludes this mini lecture. We've looked at continuous random variables, and we've looked at continuous random probability distributions and how to do some simple tasks with them. The next lecture is going to look at the properties of these distributions in more detail. For example, how we calculate the mean and variance of a distribution, and how we can transform the mean and variance. Thank you very much.